Chapter 4, Moving Charges and Magnetism. In last lecture, we have discussed what is solenoid, how solenoid is formed, how it is working, magnetic field inside solenoid, its equation. Okay. Now, today we will see the toroid. The toroid. What is toroid? Again, it is used to find, or it is used to obtain magnetic field. Now, what is toroid? See, first of all, what is definition? The toroid is a hollow circular ring on which a large number of turns of a wire are closely wound, like this. See, if we have a hollow, ring like this. The toroid is a hollow circular ring on which a large number of turns of wire are closely wound. Okay, large numbers of turns of wire are closely wound. They are closely wound like this. Okay, so yes, it is called toroid. Clear about this? The toroid is a hollow circular ring on which a large number of turns of wire are closely wound. And yes, that current is flowing from it. That current I is flowing from it. So yes, current is flowing from each and every turn. Clear? What is second definition of toroid? It can be viewed as the solenoid which has been bent in a circular shape to close on itself. How? See, for example, it is solenoid. Clear? Now if I take this two end and I join these two ends. If I connect these two ends of solenoid, then obviously it will be like this. It will become like this. Yes, it is called solenoid. It is called toroid. So yes, how toroid is formed? First case and it is second case. Now, in case of solenoid, you have to find what is magnetic field. See here, if current is flowing in this direction, I, then we know, we have discussed in last lecture, current is flowing in this direction, then magnetic field is parallel to axis in this direction. Yes or no? Magnetic field is parallel to axis in this direction. Now, if this toroid is made of this solenoid, like this, okay, and current is flowing in this direction, and see, current is flowing in this direction, then here, magnetic field inside this solenoid, inside this toroid, it is in this direction. It is direction of magnetic field. So see, the direction of magnetic field inside is clockwise when current is flowing in this direction. Clear about it? Okay, so yes, you have to remember, in case of toroid, inside core, see, it is called core. Inside core, magnetic field at each point is in tangential direction. Clear about this? It is in tangential direction. At this point, magnetic field is in direction of tangent. At this point, it is in direction of tangent. So yes, in toroid, inside core, magnetic field at each point is in tangential direction, while outside core, okay, means this side. See, It is outside. Outside, see, we know last lecture we have discussed. In case of solenoid, there is magnetic field only in this inner region, okay, interior part. Outside of solenoid, what is magnetic field? Zero. So obviously, in case of toroid, in this region, that is outside toroid, magnetic field is zero. Also, the space surrounded by toroid means in this region, magnetic field is zero. Okay, in space outside core, magnetic field B is equal to 0. Space surrounded by toroid. In space surrounded by toroid, again magnetic field is 0. Magnetic field is only inside this core. Magnetic field is only inside this core. And what is direction of magnetic field? Inside core, magnetic field at each point is in tangential direction. So now we have to obtain what is magnetic field at each and every point. So yes, what we will do, see, from this center, I am taking its average radius. Let it is R. Average radius R. Okay, and I am taking 1 ampere loop having radius R. 1 ampere loop having radius R. Okay, so yes, take a loop having radius R, as shown in figure. Having radius R as shown in figure. Clear about this? Now, for this loop, we have to apply Ampere's circuital law. Apply Ampere's circuital law. Apply Ampere's circuital law. What is Ampere's circuital law? Integration B dot dl is equal to mu 0 sigma I. Mu 0 sigma I. Clear about this? First of all, we will discuss about integration B dot dl. See, integration B dot dl is equal to integration B dl cos theta. Now what is value of theta? See, in case of toroid, inside core, magnetic field at each point is in tangential direction. Why tangential direction? Again, solenoid, magnetic field is parallel to axis. If I bend this solenoid to make toroid, then observe this line. Observe this line. It will be like this. Yes or no? So in case of toroid, magnetic field at each point is in tangential direction. Or if you consider individual loops, for this loop, magnetic field in this direction. For this loop, magnetic field in this direction. For this loop, magnetic field in this loop direction. For this loop, current is going in this direction, magnetic field in this direction. So yes, you can also verify direction like this. Yes or no? Yes it is. Okay. Due to each and every loop, find direction of magnetic field. It will be in this direction. Ampere loop, it is also in this direction. Yes or no? Yes. See, it is ampere loop. Then B dl cos 0. What is value of cos 0? Yes. What is value of cos 0? It is 1. So it is integration B dl. B constant. Inside at each and every point, magnetic field is uniform. So here it is integration B dl. Now dl means length of element. Yes or no? So what is integration dl? Circumference of this circle. Its radius is r. So I can write it as P into 2pi r. Clear about this? Okay. Now right hand side, mu 0 sigma. Mu 0 as it is sigma I. That is total amount of current. Now number of turns. Yes, I am assuming number of turns. Okay, like numbers of turns on this solenoid are n. Total numbers of turns on toroid are n. From each turn, current flowing is I. So what is total current? So therefore total current sigma I is equal to it is Ni. Clear about this? Now use this equation again. Integration d dot dl is equal to mu 0 sigma I. So here it is b into 2 pi r divided by mu 0 Ni. So b is equal to, here it is mu 0 n upon 2 pi r I. Clear about this? And total numbers of toroid, 2 pi r. 2 pi r is circumference. Length of toroid, we can say 2 pi r is length of toroid. Numbers of turn divided by length of toroid. Numbers of turn divided by length of toroid. It is nothing but numbers of turn per unit length, small n. So yes, I can write this equation as b is equal to mu 0 Ni. B is equal to mu 0 Ni. Where what is small n? Small n is equal to n upon 2 pi r. Numbers of turns per unit length. Numbers of turns per unit length. If you have marked, what is equation of solenoid? B is equal to mu 0 Ni. What is equation for toroid? B is equal to mu 0 Ni. But there is one change. In a case of solenoid, yes, in this case, what is small n? Small n is total number of turns per unit length. See, linear means it has length L. It is toroid means circular. Toroid means circular. Then what is its length? Its length is 2 pi r. Its length is 2 pi r. So what is difference? Difference is of n. That is numbers of turns per unit length. Clear about this? So it is all about toroid. Two important topics in this chapter: solenoid and toroid. Why they are used? They are used to obtain magnetic field inside core. Magnetic field inside core. Clear about this? Now we will see some questions. Yes, questions based on solenoid and toroid. Yes, simple. See, you are given one solenoid having length 0.5 meter and radius 1 centimeter. Okay. Numbers of turns, n is equal to 500. I, current flowing from it, is 5 ampere. And you have to find what is magnetic field inside. See, length is 0.5 meter and radius is 1 centimeter. So yes, we can say it is long solenoid. It is long solenoid. And in case of long solenoid, magnetic field inside. What is equation of magnetic field inside? B is equal to mu 0 small n. Solenoid means mu 0, n means capital N upon L. Clear about this? So yes, mu 0, you know what is value of mu 0? B is equal to, it is 4 pi into 10 raised to minus 7. Total numbers of turns 500. Current flowing, it is 5 divided by what is length? It is 0.5. So you can easily calculate what is magnetic field. Clear about this? Next question is exercise 4.17. You are given a toroid core having inner radius 25 centimeter and outer radius 26 centimeter. Total numbers of turns on core, they are 3500 and current flowing is 11 ampere. You have to find magnetic field first outside the toroid, inside the core of toroid, and see that is in the empty space surrounded by toroid. See, if you draw toroid, hollow circular ring, okay, yes, inner radius, it is R1, outer radius, yes, it is R. Clear about this? Okay. Turns on solenoid. Clear about this? And current is flowing from it. What is question? Inner radius 25 centimeter. So yes, I can write R1 is equal to 25 centimeter. Outer radius, it is 26 centimeter. Clear? Okay. N is equal to 3500, Y is equal to magnetic field outside toroid. Outside toroid means this region. It is called outside toroid. And yes, from theory we can say that outside toroid magnetic field B1 is equal to, it is 0. Yes, you have to write directly because there is no magnetic field outside toroid. Simple. Second question, inside the core of toroid means in this region. Yes, in this region there is some value of magnetic field. What is equation of magnetic field? See, what is equation of magnetic field? I will write here. It is B is equal to mu 0 Ni. We have obtained B is equal to mu 0 Ni. What is value of N in case of toroid? Mu 0 total number of turns divided by 2 pi r into I. Mu 0 4 pi into 10 raised to minus 7. N given, I given, 2 you know, pi you know. What is R? See, you are given inner radius and outer radius. So yes, to find R, you have to take its mean average. You are given R1 25 centimeter, R2 26 centimeter. How to find R? R is equal to R1 plus R2 divided by 2. Okay, so yes, it is 25 plus 26 divided by 2, and you know that it is nothing but 25.5 centimeter. Clear about this? So which value of R you have to consider? R is equal to 25.5 centimeter. Now you are given each and every data. Mu 0 4 pi into 10 raised to minus 7, N 3500, I 11 ampere, 2 pi as it is, and value of R is 25.5 centimeter. You can easily find. Okay. Third question, question number C. In the empty space surrounded by toroid, means in this region, students, in this region. Okay, it is question number A here, it is question number B here, and here it is question number C. In this region, then again in this region, what is magnetic field? In this region, magnetic field V3 is equal to, it is 0. It is 0. Clear about this? Next question, exercise 4.8. A solenoid 80 centimeter long, having 5 layers of windings, 400 turns each. In one layer there are 400 turns. Such 5 layers are given. So total numbers of turns means total numbers of turns N is equal to 5 into 400. Means it is 2 0 0 0. Simple. Okay. Length of solenoid N is equal to 80 centimeter is equal to, I can write 0.8 meter. Yes, it is. Okay, current I is equal to given 8 ampere, and you have to find what is magnetic field inside. It is given solenoid. For solenoid, see again, 80 centimeter long, 80 centimeter long, diameter 1.8 centimeter, means radius is 0.9 centimeter, means this length is large comparative to its radius. So yes, it is again long solenoid. It is again long solenoid. And for long solenoid, what is equation of magnetic field inside? B is equal to mu 0 Ni is equal to mu 0 N upon L. Mu 0 4 pi into 10 raised to minus 7, N 2000, L 0.8, I you are given. You can easily calculate your answer. Clear about this? So yes, in today's lecture we have discussed about toroid and some questions based on solenoid and toroid. Clear? Students, watch regular videos, make notes, and try to solve your doubts. Okay? And yes, you have to give compulsory each and every exam on Monday, Wednesday, and Friday. Okay? And yes, do not forget to share, subscribe, and comment on video of each and every teacher.